Um, Hello everyone. Good evening. So this is the tutorial session 11th for the NPTEL course on variation calculus and its applications in control theory and mechanics. So in this session, now we'll begin a two-part, or if possible, three-part series on the reviewing of whatever has been taught in the entire course. So in the tutorial session today, we will be covering the first half and first half of the course, and then in the next and maybe one more we'll be reviewing and covering the rest of the remaining part of the course. So yeah, it's me, Jia Krishnasan Avatar, a PhD student at Indian Institute of Science, Bangalore. So let's begin with, I won't be reviewing the theory part per se for the first 6 weeks, because we do have a lot of theory and what I believe is, if you would really want to go through the theory, then even the summary part, you could please review my first 6 tutorial slides, tutorial presentations. That would be well enough. So I would be reviewing the first 6 weeks here through solved examples. And here we would be covering Euler-Lagrange equations and the generalization of Euler-Lagrange equations, the some of the isoperimetric problems, and then problems with holonomic and non-holonomic constraints, followed by problems with Brocken extremals, or whose solutions are Brocken extremals, and we will be also discussing the Hamiltonian formulation. Okay, so let's start with first question for the day. The question is, extremize Jy is equal to A to B y squared or plus y prime squared plus 2y to the power x dx, and determine the general solution of the extremizer. Okay, let's solve this. So at first, let me just write on just for the sake of so that you recall the standard form of a very uh, simple functional, which is j of y is equal to a to b f of x y prime dx. So comparing this with the above expression, or for the given functional here, f is equal to y squared plus y prime squared plus 2y to the power x. And let's find the general solution of the extremizer. And you know that the extremizer, or the necessary condition for extremizer, is obtained by solving the Euler-Lagrange equations, right? And this is given by d by dx of partial f with respect to y prime minus partial f, that's a single derivative, partial f by partial y is equal to 0. For the given case, we have d by dx of partially with respect to y prime is 2y prime minus partial f of with respect to y is 2y plus 2 e to the power x is equal to 0. And then factoring out 2, we have y prime minus y plus e to the power x is equal to 0. And we can write this in a, just for the sake, we can write in this form, so that all the terms containing y are on the left hand side and the rest on the right hand side. Now, upon solving this, you know that there is a second order inhomogeneous. Second order, first of all, it's linear and inhomogeneous ODE, right? Or indifferential equation. Okay, let's solve this. So it's, we have y double prime minus y is equal to the power x. And you know that since it's a non-homogeneous problem, it has to have the solution yx has to be solution of addition of or some sum of two solutions, which is the solution to the homogeneous, to the corresponding homogeneous problem, and a pure what we call as a forced problem, or the particular integral, that's what we call, right? So for this, for solving yhx, we need to construct a homogeneous version. So it is y double prime x minus x is equal to 0. And the general solution is you know very well, right? That it will be c1 e to the power x plus e to the power minus x. Now for the partial integral, and mind you that the roots, or I'll just leave it here. Okay, for ypx, we need to have yp double prime x minus yp of x is equal to the power x. Now, when you take a look at the forcing function for the equation here, which is e to the power x, this is the same as one of the eigenfunctions, or the one of the independent solutions to the homogeneous problem, homogeneous uh, construction of the problem, right? So what we can conclude from here is that obviously we cannot have a solution which is, and you know, the way we solve a for the particular integral of a problem, right? That we will construct an assumed solution which is of the same form as the given as the forcing function, which is e to the power x here. But since we already have the forcing function as one of the independent solutions, so we cannot do that. We cannot take the same. So instead of that, what we take is, let's try to construct an ansatz problem. Let's take an ansatz for this problem as take yp of x is equal to, say, and the simplest possible linearly independent problem, independent solution, right, which is x e to the power x. So that our task is to determine the value of c. Fine. Now let's take the first derivative of this, and this gives us c to the power x plus c x e to the power x, and then yp double prime, the single prime and the double prime of yp is c e to the power x plus c e to the power x plus cx, and this is given as 2c to the power x plus cx e to the power x. Okay, let's substitute this in our original problem, such that we have 2c e to the power x plus cx e to the power x minus, and then yp is e to the power x, x is equal to power x, right? And then this cancels out, so that we have 2c to the power x is equal to power x. And for this to be equal, we need to have 2c is equal to 1, and this implies that c is equal to half. So therefore, our yp is, particular integral is x by 2 e to the power x, isn't it? So therefore, the general solution of the extremizer is yx is equal to, or the extremizer is y as a function of x is equal to c1 e to the power x plus c2 to the power minus x plus x e to the power x by 2. Okay. Now let's solve the next problem in this sequence. Let's take a problem whose does that. Now let me write the problem first. Find the general form extremals for the functional. And the functional is j y is equal to 0 to pi by 2 y double prime squared minus y squared plus x squared dx. Okay. And what you say is that in this case, our f, so this here, f is a function of x, y, and let's put the general, let's take all the derivatives up to the one that we have in the expression here. So y prime, and then also y double prime, isn't it? So this is a problem with, isn't it? It has higher order derivatives. So the generalized, so we need, this is a generalized or we need the necessary condition for the extremal, extremizing the functional would be given by the generalized Euler-Lagrange function or Euler-Lagrange equation, sorry. And this is given as -1. Since we have derivative up to 2, so we'll have -1 square d squared by dx squared of partial L with respect to partial y double prime minus, or I can still write as +1 to the power 1 plus -1 to the power 1 into this dx, sorry, d by dx of partial f by partial y prime, and then plus partial f by partial y is equal to 0. Okay. Now let's -1 raised to the power 2 is just 1. So we'll have d by d square, and then partial f with respect to y double prime is 2y double prime minus d by dx of partial f with respect to y prime is 0 plus minus 2y equal to 0. Okay, and then what we have here is 2 into y to the power 4, or y 4 derivative of y, sorry, 4 derivative of y minus 2y is equal to 0. Such that, and factoring out 2 gives us y 4 minus y is equal to 0, isn't it? Now, the general solution to such problem, I'm sure you know how to solve it, so I'll be solving that. General solution to such a problem, it's a fourth order linear homogeneous ODE, right? And you know how to solve it. So all you have to do is you have to put y is equal to e to the power mx as the test solution, and then determine the value for m, which is the exponent multiplied with x, isn't it? So the general solution here is y of x is equal to a cosine hyperbolic x plus b sine hyperbolic x plus c cosine x plus d sine of x, and this is our general solution. Okay. Now let's go to our next problem in the sequence. And so the next problem in the sequence is Okay, so the next problem is find the extremal of the functional jy 0 to 1 plus y prime per dx. Satisfying basis is equal to 0, y prime 0 is equal to 1, y1 is equal to 1. Okay. So, so again, it's a case of a generalized Euler-Lagrange equation, right? So and the solution is, let's first find the Euler-Lagrange equation. And from the previous, we recall that it will be d square by dx square minus d by dx okay, and then this implies that partially with respect to y double prime is nothing but 2y double prime, isn't it? And then minus dy by dx, and there is no term with y prime, so 0, and then there is no term with y also, so it's 0 again. So this implies that we have d to the fourth derivative of y, right? Okay, now let's integrate 4 times or integrate the above equation 4 times with respect to x 4 times. Okay, so first integrating first gives us, and then second gives us third gives us and fourth integrating it once more gives us or just y of x is equal to ax cubed by 6 plus bx squared by 2 plus cx plus d, right? So a, b, c, d are the integration constants or the constants of integration. Now let's put the boundary conditions, apply basis. Okay, and so y0 is equal to 0. This implies that d is equal to 0. Likewise, y at or y prime at 0 implies that c is equal to 0. Okay, now we have y prime at 0 is equal to 1, and this implies that a by 2 plus b plus c is already 0, so is equal to 1. Sorry, and that's so, and then sorry, why this is 1, right? Sorry, this is 1. So plus 1 is equal to 1, is it not? And then y prime at 1 is equal to 1. No, I think there I have made some mistake here. No, it's all right. It's all right. So it's y at 1 is equal to 1, and y at 1 is equal to 1 is a by 6 and b by 2, and okay, fine, this is done. And then y prime at 1 is equal to 1 implies that a by 2 plus b plus 1 is equal to 1, right? And then upon solving the first expression, we just have, I'll take multiply throughout by 6. And we have is a plus 3b is equal to 0. And from the second equation, we have, let's multiply throughout by 2. So we have a plus 2b. And what you see clearly from here is, if we subtract the second from the first, we have b is equal to 0. And then when b is equal to 0, a is equal to 0. Essentially, therefore, the solution is y of x is equal to x. This is the extremal of the problem satisfying the boundary conditions. Okay. Okay. Now let's go into the problem when the case of multiple independent variables, right? So let's take up a simple problem. It says that obtain the extremizer of the functional and we need to externalize this functional. So this is a problem. Well, let's just call the integrand as f. So f has two independent variables, right? And one dependent variable, which is phi. And you know that it also contains higher order derivatives. Essentially, it's a problem of generalized Euler-Lagrange equations, where the highest derivatives are of order 2. Okay. Then let's find the Euler-Lagrange equation. The Euler-Lagrange equation is phi minus and mind you that the subscripts of xy of phi represents the derivatives of phi with respect to that subscript. Okay? It's just a sorted notation, and then there is no term containing phi x, right? So we'll have 0. And then there is no term containing phi y. This is also 0. And then this derivative with respect to phi double x is 2 into phi xx plus with respect to xy is phi xy is 4 into pxy, is it not? And then plus 2 phi yy equal to 0. Okay. Now what we do is let's factor out 2 throughout. So we'll have if you recall it, this is what is widely known as biharmonic equation. It has you can come across this equation in various different forms in various areas of engineering and science. In mechanics, it does tend to have a particular name. It's known as the Aries function, and this is in plane stress and plane strain problems. Plane strain problems in solid mechanics. We call this equation as Aries equation. Aries equation, and the solution to this Aries equation is we call it as Aries function. Is given by phi. Okay, now let's go to the next problem in this sequence. There is a problem with respect to univariate optimization. For the this problem is find the dimensions of a cylindrical tin with top and bottom made of sheet metal. To maximize its volume such that the total surface area is equal to A naught is equal to 24. Okay. Let us create a schematic of the problem as to how does it look. This is a cylindrical thing. And let's denote its radius as x1. And the height as Okay. Now we need to maximize its volume, isn't it? We need to maximize its volume. Now the volume is V, and you know the value of a cylindrical of a right circular cylinder, right? It's pi into radius square, which is x1 squared, and height, which is x2. Okay, and these are volume, expression for the volume, and subject to this is an optimizing problem. So we need to write in the canonical form that we use for denoting the for expressing a mathematical optimizing problem. And the subject to it's this total surface area, and the total surface area is given by 2 pi into the area of both the disk, so to speak, the top and bottom faces of the right circular cylinder. So it is both are circles, right? So the area is pi into radius squared. So pi x1 squared for one of them, and for both we have 2 pi x1 squared. And for the circular part or the of the cylindrical part, so to speak, we have 2 pi x1 into x2, and this has to equal to 24. And these are equality constraints. Now what we do is let's substitute x2 and let's determine x2 in terms of x1, right? And this helps us to simplify our problem. Then this implies that after factoring out 2 pi from both sides, we have x1 squared plus is equal to 12, isn't it? Let's write x2 in terms of x1. So x1, x2 is equal to 12 minus x1 squared. And this implies that x2 is equal to 12 minus squared by x1. And this is given by 12 by x1 minus x1, right? So therefore, substitute this we call as C in A to give 12 pi x1 minus cubed. Okay. And what you see is now V is a pure function of x1, right? It's a function of x1, is it not? So what we do is let's let's apply the necessary condition for extremum. And this given by dv by dx1 is equal to 0. And this implies that 12 pi minus 3 pi x1 square is equal to 0. And this implies that, what does this apply? This implies that we'll factor out 3 pi from both sides. So we'll have x1 squared is equal to 4. And this implies that x1 is equal to plus minus 2. Now you see, and since we denote the extremals of a particular function as x star in optimization, so
what we see is x1 star is equal plus minus 2. However, x1 star cannot be less than 0, right? So then because we cannot have radius to be as a negative or radius as a negative number, so this implies that x1 star is equal to 2. Fine. And therefore x2 star, which is the height, is given by 12 by x1 star minus 1 star. This given by 12 by 2 minus 2, and this gives 6 minus 4. So therefore, x1 star, x2 star is equal to 2 comma 4. And we are saying that, okay, and let's also try to okay. So let's determine whether this extremal does it this extreme does it maximize minimize our functional, right? Or our function here, which is v. So let's find the second derivative. Check the nature extremum. So what we do is let's find the second derivative of v with respect to x. And this gives us minus 6 pi x1. And this at second derivative of v with respect to x1 square at x star, I'll just call it x vector star, is equal to minus 6 pi x1 star, and this is given by minus 12 into pi. This is less than negative. So this means that v is maximum at x vectors star. So therefore, the maximum, so the dimensions are dimensions of the cylinder which maximizes the volume, ensuring that the total surface area remains at 24 pi. Radius is equal to 2 and height is equal to, okay. So these are the values of the extremum, or the dimensions. Okay. Let's solve another one. With regard to when we use the problem with constraints. So the question says that find the extremals of the functional index j of y is equal to 0 to 1 square plus x square subject to the okay. So we have a functional here j of y and it's subject to whose x with certain constraints on the extremizer, which are y is 0 at 0 is 0 and y at y is equal to 1, as x is equal to 1 is 0. And we also have a integral constraint on the extremal, which is given by iy. Let's construct an auxiliary function at first. F of y is equal to j of y minus lambda iy minus 2. And this lambda here is a Lagrange multiplier. And this is to ensure the satisfaction of the constraint, okay? And this will write it as 0 to 1 plus x squared y squared plus 2 lambda. And the integrand of the there is a mere constant. Although lambda is to be evaluated, but still it eventually comes out to the constant. Okay. So the Euler-Lagrange equation is what? D, it's d by dx of Hausler with respect to y prime to y is equal to 0. This implies that to y prime minus of minus 2 lambda y is equal to 0. Factoring out 2 gives us plus lambda y is equal to 0. Now we can have 3 possibilities for lambda. Lambda is equal to 0 is y double prime is equal to 0, right? And this gives us yx is equal to c1x plus c2, where c1 and c2 are the constants of integration. And let's determine c1 and x2 using c1 and c2 from the boundary condition. Now y at 0 is equal to 0 implies that it is equal to. Likewise, y1 at 1 has to be 0. This implies that c1 is equal to 0. So this means that y is equal to is equal to 0. This is simply a constant function. However, you see that this doesn't satisfy I of y is equal to 2, right? Because the thing is, in this case, y square over dx is nothing but 0. So therefore, lambda is not equal to 0. This is the first conclusion. Second, let's suppose lambda is less than 0. Then this implies that we can write lambda is equal to minus some. So wide, and here omega is greater than. Okay. Now we'll write this as y prime minus omega squared y is equal to 0. This implies that y of x is equal to c1 to the power omega x plus c2 to the power minus omega x. Okay. Now let's look at the boundary conditions. Y of 0 is equal to 0. This implies that c1 plus c2 has to be 0, and this means that c2 is equal to minus c1. Okay. If there is y1 is equal to 0 is 0, then this means that what we have is c1 to power omega minus to power minus omega. Is it not? Is equal to 0. So what we see here is either this is equal to 0 or this is equal to 0. But e to the power omega minus e to the power omega is never equal to 0. Unless omega is equal to 0, but omega is greater than 0, right? So as omega is greater than 0. So therefore, c1 has to be 0. This implies that c2 is equal to 0. Then again, y of x is equal to 0. It doesn't satisfy iy is equal to 2. So therefore, lambda isn't equal to 0. So the only condition we have is y lambda is greater than 0. And this implies that lambda is equal to omega squared and omega is greater than 0. Is it not? And then what we'll have is y double prime plus omega squared y is equal to 0. And this implies that y of x is equal to c1 to the power omega x plus c2 to the power minus omega x. Okay. Now using boundary conditions which are y is equal to 0 is equal to 0, this implies that sorry, this shouldn't be this. I'm sorry. I think it will be a cos omega x plus b sin omega x. Okay, and then what we have is y of 0 is equal to 0. This implies that a is equal to 0, fine, and then y of 1 is equal to 0. This implies that b sin omega is equal to 0. Now in this case again, either b is equal to 0 or sin omega is equal to 0. But again, this is not possible. Why? Because again, it will lead to a trivial solution. So this implies that sin of omega is equal to 0, and this means that omega is equal to n pi, and then n is an element of set of integers. Therefore, our y of x is equal to b sin n pi x. Okay. Now to determine b, we need the isoperimetric constraint. Perimetric constraint. Okay, and then this is given by y of y is equal to 0 to 1 y squared dx is equal to 0 to 1 b squared sine squared n pi of x. This means that b squared, and then using trigonometric identity, we can convert this into a cosine function. So 1 minus cosine 2n pi x divided by 2 dx is equal to 2, is it? And then this implies that we'll integrate this b squared by 2, and then this comes to be x minus sine 2n pi x divided by 2n pi 0 to 1 is equal to 2. And here you see that this comes to be 0, sorry, 1, 1, and 1 minus sine 2n pi by 2, again 0, minus of 0 minus again sine 0 by 2n pi is just 0. So essentially we have b is equal to b square is equal to 4, b is equal to plus minus 2. So therefore our expression for extremal is y of x is equal to plus minus 2 sine n pi of x, right? And then n is the set of sorry, it's just a set of integers z. Although in this case we can even have it to be the set of non-zero integers, but let's leave it at that. Fine. Now let's look at some more problems in this series. Let's have the following problem. The question says that find the curves for which the functional is equal to 0 to x1 square divided by y dx with y0 is equal to 0 can have extremal if the point can vary along the line x minus 5. Supposed to draw the schematic of this problem, is it not? So we have a point from the origin, and we have y is equal to x minus 5 is, let's draw the coordinate system. Y is equal to x minus 5 is when x is equal to 0, y is equal to minus 5, right? we have this these are x. This intersects at 0.4 These are line y is equal to x minus 5. So it says that we need to determine a curve such that one point of the function lies on the domain of the function is from 0 to x1. So one point is fixed, which is 0, and the other point is x1, which can lie anywhere on this. X1 can lie anywhere on this line, which is x minus 5. So it's a problem. It's a problem of a variable endpoint. Problem. And to solve such problems, we need to invoke what we call as the transversality condition, right? Yeah. So in this case, the integrand of the functional I is root over 1 plus y prime squared divided by 1. And what we say is f is independent of explicitly. I need to make this clear. Independent of x. So we can use what we call as this Beltrami identity. Is y prime del f by del y prime minus f is equal to c. Now y prime into del f by del y prime is 1 by y into 1 plus y prime squared minus this comes again to 1 plus divided by y is equal to c, and c here is a constant. C is constant. This needs to be determined later. Okay, and then what we do is let's take 1 by y is common, and then we have something called as y prime equals to y prime. So y prime square divided by 1 minus y prime squared minus 1 minus y prime squared equal to constant, and this what we say is this comes out to be this comes out minus 1 divided by y into root over 1 plus y prime square is equal to constant. And then we can take negative on the other side. So this will also call as c, just because this constant needs to be determined eventually. And then even y into 1 plus y prime square is also, let's call it at the same time, which is squaring both sides. We have y square into 1 plus is equal to c. Okay. And then this implies that y prime squared is equal to c by y squared minus 1. Okay. So that we have y prime squared is equal to c minus y squared by y squared. Let's take square root. Then we have y prime equal to plus minus. And let's only take positive square root. I'll call it just for the sake to root over c minus y squared divided by 1. Is it not? And then you have separation of variables, so it comes to be y dy by root over c minus y square. And then make some substitutions. Take z is equal to minus y square. Dz is equal to, or minus dz is equal to 2y. So this implies that dy y dy is equal to minus z by 2. So this means that what we have is minus dz by 2 into my root over z is equal to dx, right? And then upon integrating it, what we have is minus half, and then z minus half plus 1 divided by minus half plus 1 x plus another constant c1 or c2. Let's call it to be c2. And then this comes out to be half. So it's nothing but minus of root over z, is it not? So we'll just call it minus c y square to half is equal to x plus c2. Okay. And then let's take squaring on both sides. We have is c minus y square is equal to. So now we have two constants. C1, sorry, C and C2. Now use the endpoint y at 0 is equal to 0. So this implies that c minus 0 is equal to 0 plus c2 squared. So this means that c is equal to c2 squared. Okay, let's keep it with us for now. And then let's substitute it here. So this implies that c2 squared minus y squared is equal to x plus c2 whole squared, and then this gives us to be minus y squared x squared plus 2c2x. This cancels out, and this leaves us with y squared is equal to minus 2c2f minus cx squared. Therefore, y is equal to root over minus 2c2x minus x squared. C2 needs to be 0.5. Now we need to invoke what we call as the transversality condition, right? We know that x1, y1 lies on what? Y is equal to x minus 5. Now let's parameterize. So, and this we call as let's parameterize. This will be called as curve gamma is equal to y. Let's just call it like this. So let's parameterize gamma as any point or any parameter in terms of this parameter z, zeta. This will give us the x coordinate is always say zeta, and then the y coordinate, let it be zeta minus 5. Okay, such that dx by d zeta and dy by d zeta is equal to 1, 1. Okay. The transversality condition is given as p dy by d zeta minus h at x1 is equal to 0. Now let's determine p. So p is y prime divided by y into and h. This we know from our Butrami identity itself, right? That is given by -1 divided by 1 into y into root over 1 plus y prime square. Is it not? So then this implies that y prime y at 1 plus y prime squared into 1 minus and then minus into minus of plus y1 by y into 1 plus y prime squared into, and again it is also at 1 all at x is equal to. Now what we see is y prime. We clearly see from here that y prime square is y prime is equal to root over y prime is equal to root over c minus y squared y squared to be minus y squared by y. Is it not? And so what we do is let's substitute this here. Y prime plus 1 divided by y into root over 1 plus y prime squared is equal to, but all at x1. So this means that, and you see the denominator, that this is always great. This term under is always greater than 0. And y we can bring on the other side. So this implies that y prime plus 1 at x1 is equal to 0. Is it not? And then this we can clearly say that I think I have missed something here. Y prime is equal to -1 at x1, right? Now what we see is y is given as, we know from here the final expression was given as in terms of 2c2x minus x2 square. This implies that y prime is equal to 1 by 2. So 2 into root over minus 2c2x minus x square. And upstairs we have, in the numerator we have minus 2c2 minus 2x, and this comes to be minus of c2 plus x divided by minus 2c2x minus x minus x square. Okay, so this means that c2 of x divided by root over minus 2c2 of minus x squared at x1 is equal to -1. Okay, and there is something known as continuity, isn't it? We'll have something known as continuity condition. And this is known as also called as the point of intersection should be the same, is it not? Which means that x1 comma y1 for the extreme measure should be the same as x gamma, y gamma, or the parametrization, so to speak, at x1, is it not? But what we see is that gamma is already gamma, so what we'll have is that x1 is already equal to x gamma at x1, right? This is the same. So this implies that y1, let's find out. So y1 is equal to minus c2 x1 minus x1 squared is equal to x1 minus 5. This is our second condition. Now what we see from the equation that we had just derived is that C2 plus x1 divided by root over minus 2C2 minus x1 squared is equal to x1 minus 5, is it not? And then, no, this is equal to 1. And then this is equal to this, we can say that the term, the term in the denominator is C2 plus x1 divided by how much? So minus 5, and this is equal to 1. So this means that C2 plus x1 is equal to x1 minus 5. X1 cancels out, so C2 is equal to minus 5, is it not? So therefore, what we have here is y of x is equal to minus 2 into minus 5 is 10, so it's 10x minus x. These are extremes. Then we can, since we are taking both the square roots, square root of plus or minus 1. So let's take it as the solution will be plus minus. Okay. Solve one more problem. The problem says that find the extremes of the functional j of y is equal to 0 to 4 y1 minus 5 plus 1 whole square into dx. And the bounding conditions are y is equal to 0 is equal to 0 and y4 at 2. And which has just one corner. Mhm. Let's solve this problem. So in this case, our f is equal to this, we can write it as y prime squared minus 1 whole squared to the part. The EL equations in this case are no. You see that f is independent of y, so there is 0. So that we have del f by del y prime is equal to constant. C is a constant here. And then this comes out to be 2 into y prime square minus 1 into 2 into y prime is equal to C. And then this we have as not 0, this we have as C. And then we can write it this as y prime into y prime squared minus 1 is equal to, I'll abuse the notation C. So this is our extremal. And what we need to do here is, let's take for our simple case, let's take C is equal to 0 at first. So then we have what we have is y prime is equal to 0, or in a sense y prime into y prime square minus 1 is equal to 0. So this means that y prime is equal to 0, or y prime or y prime square is equal to 1. So this means that y is equal to some constant. Let's call it as E constant. And this implies that y prime or y prime is equal to plus minus y, right? Plus minus. So this means that y of x plus minus x plus d, and d is a constant. D is constant. Fine. Okay. And the problem already says that we have a solution from 0 to 4, and the domain is 0 to 4. And now we can have some constant here, and then there is a corner point at x star. And we need to determine the Poisson of star, and there's our solution y1 and solution y2 from the segments. Okay, now let's invoke our corner conditions. Corner, or what we also call it as Weierstrass Erdmann condition. The condition is that the condition that we have here is, first of all, we have P at y1 of y1 at x star is equal to P at y2 of x star. And the condition 2 is h of y1 at x star is equal to h of y2. Let's determine the expression for P, and P is equal to partial f by y prime. Okay, and this comes out to be 4 into y prime into y prime square minus 1, and h is equal to y prime p minus f. Right? So what we have here is y prime is given as prime into 4, so it becomes 4y prime squared into y prime squared minus 1 minus of y prime squared 1 whole squared. And this we can write as square minus 1 and then 4y prime squared minus y prime squared plus 1, right? And then this comes out to be 1 into 3y prime squared plus 1. Okay, that is equal to this. Now check our first condition. First condition says this was our conditions, right? So P at y1 at x star is equal to P of y2. Fine. So this comes out to be y prime into y prime, well, this y1 into at x star is equal to 4 y2 prime square. Now what we clearly see is we had the conclusion of in this case to be either y prime is equal to 0 or y prime square minus 1. So for both the cases, it always comes out to be 0, and there is also. So this first condition is easily satisfied. What we need to worry is the second condition. Okay, the second condition says that h at y1 1 prime at x star h of since h is a function of both y1 and y prime. We should live like y1, y2, and y2. Okay. So this has as y1 square minus 1 and plus 1 likewise y2 squared minus 1 y2 prime, sorry, y2 prime, right? y2 prime squared into 3 y2 prime squared plus 1 at x star. Okay, let's expand the terms on both the sides to get as y1 prime squared minus 1 into plus y1 prime squared minus 1 likewise y2 prime squared minus 1 into plus y2 prime squared plus minus 1. Minus 1 cancels on both sides. And what we can do here is let's also expand this term. So here y1 prime to the power 4 minus 3 into y1 prime squared plus y1 prime squared, right? Likewise 3y2 prime to the power 4 minus 3y2 prime squared plus y2 prime squared, right? And this gives up to be 3 into y prime to the power 4. And let's bring one, this evaluates to minus 2, right? Minus 2 y prime square, and this also to be minus 2 y prime, y2 prime square. So this gives up to be 3 into y prime, y1 prime to the power 4 minus y2 prime to the power 4 minus 2 into y square, 2 prime square is equal to 0. And this gives this comes y1 square square minus y2 prime square, taking this to be common, and then we have 3 into y1 prime square plus y2 prime square minus 2 equal to 0. Now you clearly see here is that y1 prime is either 0 or 1. And before that, so this time can either be even in the extreme case, right? This is either is 0 or 1, is it not? 0 or 1, and this is also 0 or 1. And even for all the possibilities, what we have is this entire term is never 0, is it not? Because if we have both zeros, then we have the term becomes -2. If we have one, just one non-zero and the other 0, then what you have is 3 minus 2, 1, which is not equal to 0. And if both are 1, then 3 into 2 is 6 minus 2, 4. It's greater than 0. So it's always non-zero. So this implies that y1 prime squared is equal to y2 prime squared. And this means that y1 prime is equal to plus minus y2 prime at x is equal to x star. Is it not? Okay. So which means that y1 prime is equal to y2 prime plus minus y2 prime at x is equal to x star. So now let's take y2 prime is equal to 1. Okay. Obviously 0 is equal to 0 is not valid, because if we have 0, then we y1 is 0. If y prime is equal to 0, then what happens is y2 prime will be 0 or 0, which means there is a and then we have to satisfy our boundary conditions, is it not? Then y0 is equal to 0, so which means that y has to be 0 throughout. So say take y2 prime is equal to 0, just for the case. Then this implies that y1 prime is also equal to 0. And since y1 prime is equal to 0 simply implies that y is a constant, y1 is a constant, a. But then again, y1 at x is equal to 0 is 0. So this means that a is 0. So which means y1 is equal to a. And then, so this eventually implies that even y2 is equal to 0, right? This is a very trivial solution. So therefore, what we do is we take, which means that y2 prime is not equal to 0. Now take y2 prime is equal to 1. Then this implies that y1 prime is equal to -1 at x is equal at x star. Okay, so this implies that y2 is equal to x plus a and y1x is equal to minus x plus b. What happens to linear equations? Okay. Now determine a and b using endpoint conditions. Okay. And then what we have is y1 of x is equal to minus x plus b at x is equal to 0, y1 is equal to 0. So this means that b is equal to 0. Now y2 of x is equal to, what was the other end condition? y4 is equal to 2, okay. x plus y at x is equal to 4, y2 is equal to 2. So this means that 4 plus a is equal to 2. This means that a is equal to minus 2. So therefore, y1 of x is equal to and y2 of x into x minus 2. Sorry, x minus 2 right here. Now, from the continuity conditions, we obtain corner point. So this means that minus x star is equal to x star minus 2. This means that 2x star is equal to 2, and this means that x star is equal to 1. Okay. So the net solution is y is equal to y of x is equal to minus x for 0 is less than x is less than or equal to 1, and x minus 2 for 1 is greater or equal to x, where x star is equal to 1 is the corner. The solution would look like no, the solution would look like, let's draw it carefully. So y at 0 is equal to 0, so here, and 1 till here, which is which is 1 here, there is 0, y, and then y at 4 is equal to 4 into 2, right? 1 and 2. What will go from it? These are solution of the problem. Okay. Yeah. The last question that I'm going to solve today is determine Hamilton's equations for Henon-Wells problem whose Hamiltonian is H p q vector is equal to half of q1 square minus solution. So the Hamilton's equations are qi dot is equal to partial h with respect to pi and I is equal to 1, 2. And the second of equation is Pi dot is equal to minus partial h qi and I is equal to, sorry, Pi minus partial h over partial qi, and I is equal to 1, 2 again. So this implies that Q1 dot is equal to partial h with respect to P1 is just one term containing P1, right? P1 Q2 dot is equal to just again one term P2, and P1 dot is equal to minus of Q1 plus 2Q1 Q2, this, okay, and P2 dot is equal to minus of Q2 plus Q1 squared minus of Q2 squared. Okay. Yeah, so I wanted to solve as many questions today. So by this we have reviewed the weeks 1 to 6 of this course, and we have also been able to cover enough review all the concepts through solved examples. So in the upcoming tutorial session, which is going to be on the 25th of April, we'll be reviewing the other parts, and we'll try if we can have one more tutorial class for an hour. Okay, so let me stop recording here. And let's meet in the next tutorial. Thanks.